Assalamualaikum warahmatullah and hi again. We'll be looking at a one-way ANOVA chapter again in this video, but in part 2. Let's proceed at how the total variability is partitioned in more detail in the following slide. To partition the total variability, we can start with partitioning the total sum of squares, which is the source of variation from the whole dataset, and can be expressed mathematically as the following equation. The main expression here is the sum of squared departures of individual observed values Yij from the estimated grand mean, and we call this as the total sum of squares denoted by SST. The SST can be expressed or partitioned into two sums of squares. The first is the sum of squared departures of the level mean from the grand mean, which we call it as the sum of squares due to the treatment levels, or the between group sum of squares, which can simply be denoted as SSTRT. The second is the sum of squared departures of the individual observed values from the estimated level mean, which we call it as the sum of squares due to errors, or within group sum of squares denoted by SSE. In short, generally we have SST equal to SSTRT plus SSE. The first two sum of squares, that is the total sum of squares SST and the treatment sum of squares SSTRT, can be further simplified as shown in the subsequent slide, whereas the error sum of squares SSE can be obtained by simply subtracting the treatment sum of squares from the total sum of squares, that is, by calculating SST minus SSTRT. From the previous slide, we had SST equal to SSTRT plus SSE. The simplified expression for the total sum of squares SST is the sum of all squared observed values Yij squared minus the grand total squared Y double dot squared divided by the total sample sizes capital N. The treatment sum of squares SSTRT, on the other hand, is the sum of squared level totals, that is Yi dot squared, divided by the corresponding level sample sizes Ni minus the grand total squared over the total sample size. Notice that the second expression in both SST and SSTRT are exactly the same. Finally, as mentioned before, the error sum of squares SSE is simply SST minus SSTRT. All these formula are provided in the statistical table booklet, page 3. After calculating the three sums of squares, the values can be tabulated in a one-way ANOVA table, which starts with the list of sources of variation. The first in the list is the factor, treatment, or the between groups, or between levels source of variation. The second in the list is the source of variation from the errors, that is, within groups or within levels source of variation, whereas the last in the table is the total source of variation. The next column in the table is the sums of squares. Please make sure that the values of the sums of squares must be placed correctly. The third column enlists the associated degrees of freedom. Similar to the sums of squares, you can start finding the total degrees of freedom given by the capital N, which is the total sample size minus 1. The degrees of freedom next is the treatment degrees of freedom given by K minus 1, where K is the number of levels, and lastly the error degrees of freedom, which is simply the difference between the total degrees of freedom capital N minus 1 minus the between levels or treatment degrees of freedom given by K minus 1. Therefore, the error degrees of freedom is simply capital N minus K. Now the next column is very important, which shows the estimates of error variance called the mean squares. The first mean square is the treatment mean square denoted by MSTRT, obtained by dividing the treatment sum of squares SSTRT by the corresponding treatment degrees of freedom K minus 1. Whereas the second mean square is the error mean square MSE, obtained by dividing the error sum of squares SSE by the error degrees of freedom N minus K. The ratio of mean square treatment and mean square error is the calculated F ratio or F test, which is the value of test statistic we are going to use in this one-way analysis of variance. Under the null hypothesis, both MSTRT and MSE estimate the unknown error variance sigma squared. However, under the alternative hypothesis, MSTRT will be larger than the error variance, whereas the MSE is still the estimate of error variance. Therefore, we can use the MSE value as an estimate of the unknown error variance sigma squared. Knowing how to calculate the test statistic, let's look at the general hypothesis test procedure for a one-way ANOVA. First, the formulation of the hypothesis statements. As explained in part 1, when we test if any of k-means is different, then under the null hypothesis H0, all the means mu1, mu2 until mu k are all equal, whereas under H1, mu I and mu j are not equal for at least one ij. Second, the decision rule is to reject H0 if the calculated F ratio, which is the F test, is greater than the right-sided critical value, which is the value of F at the whole alpha level of significance with degrees of freedom K minus 1 and capital N minus K, where K minus 1 is the treatment degrees of freedom and the capital N minus K is the error degrees of freedom. The next step is to find the test statistic, which is the calculated F ratio defined as the ratio of the mean square due to treatment, denoted by MSTRT, and the mean square due to errors, denoted by MSE, as shown in the ANOVA table just now. The final step is the decision whether to reject or not to reject H0, and the practical conclusion on whether the means are equal or not. If you are interested to test if any treatment effect exists, then the hypothesis statements will change to testing the effects instead of testing the means. Therefore, under H0, we have all treatment effects equal to 0, which means no treatment effect exists, implying all the means are equal. Under H1, however, we have at least one treatment effect is not 0, which implies at least one mean is different. The other steps in the statistical testing procedure, such as the decision rule, the calculation of test statistic, which is the calculated F ratio, and the critical value, are exactly the same as what we had when testing the means. Of course, in the conclusion, when you test the treatment effects, then you should conclude on treatment effects as well. Therefore, please be consistent from the beginning. If you test the equality of the means, please conclude on the means. Whereas, if you test the existence of treatment effects, then you should at the end conclude on the existence of the treatment effects. Please look again at example 6.1 from the Statistics for Engineers textbook on the use of 3 different types of alcohol in a particular chemical process. The question is to test whether the 3 populations appear to have equal means at the level of significance alpha equal to 0.01. As you can see, we are to test if 3, which is more than 2 population means, are equal or not. Therefore, you should use a one-way ANOVA to perform this hypothesis testing. What you need to do first is to calculate the level total and the grand total and list them as follows. You may identify also the sample size and I from every level and the total sample size capital N. Next is to calculate the total sum of squares denoted by SST. By formula, SST is given by the sum of all squared observations, in this case 93 squared plus 95 squared plus all other observations squared until the last one plus 84 squared minus the grand total squared, which is 778 squared, divided by the total sample size capital N, which is 9, giving us SST equal to 660.2222. Next, calculate the sum of squares due to treatment denoted by SSTRT given by the sum of all level total squared divided by the corresponding level size, that is 262 squared over 3 plus 279 squared over 3 plus 237 squared over 3 minus the grand total squared over the capital N. You may check that the value of SSTRT is simply 297.5555. Taking the difference between SST and SSTRT, you can then get the error sum of squares SSE given by 262.6667. Please note that the values of all 3 sums of squares must always be positive, since we have the sum of all squared values. Having calculated the sum of squares, you can then construct the one-way ANOVA table as shown in the following slide. After calculating the sums of squares, you can now construct a one-way ANOVA table for example 6.1. The first column is for the source of variation, which can either be for the factor, error, or the total source of variation. The second column is for the calculated sums of squares, followed by the third column for the degrees of freedom. The fourth column is for the mean squares, and finally, the column for the calculated F ratio or the F-test statistic value. To place the values of sum of squares in the second column, you can start with the total sum of squares SST, followed by the factor or treatment sum of squares SSTRT. The balance must be the error sum of squares SSE. Please make sure when you add up the SSTRT and SSE, you will get back the total sum of squares SST. Similarly, for the degrees of freedom in the third column, you can start with the total degrees of freedom, which is the total sample size 9 minus 1 given by 8. Next is the treatment degrees of freedom given by k minus 1, where k is 3, so that the treatment degrees of freedom is simply 3 minus 1 equal to 2. The balance must be the error degrees of freedom, which is simply 8 minus 2 equal to 6. Now dividing the second column by the third column, you will get the values of mean squares in the fourth column. Therefore, the treatment mean square MSTRT is SSTRT divided by 2, giving you this value, whereas the mean square error MSE is simply SSE divided by 6, which gives you this value. Finally, to obtain the calculated F ratio, which is simply by dividing the MSTRT by MSE, so the F ratio or the F test value is 148.7778 divided by 60.4445, giving you a value of 2.4614. After constructing and completing the ANOVA table, you can now complete the statistical hypothesis test to solve the problem in example 6.1. To complete the solution for example 6.1, you need to state the hypothesis statements and the decision rule, as well as writing the decision and conclusion which answer the question. Since you are to test if the three population means are equal, then under the null hypothesis H0, mu1, mu2, and mu3 are all equal, against the alternative hypothesis H1, where mu is not equal to muj for at least one ij, for I or j equal to 1, 2, or 3, and I is not j at the same time. The decision rule is to reject H0 if the calculated F ratio is greater than the right-sided critical value, which is F 0.0126, given by 10.92 from the statistical table booklet, page 40. Please correct the typo error in the textbook on page 132. By comparing the value of calculated F ratio with the critical value, we can see clearly that the F ratio is smaller than the critical value. Therefore, you can decide not to reject the null hypothesis and conclude at 0.01 level of significance that there is no significant difference between the three population means due to different types of alcohol used in the particular chemical process. For another example, let's look again at task 6.1 from the Statistics for Engineers textbook on page 133. In this task question, we have different unequal sample sizes. The question is to use ANOVA in order to test for the differences in the heat loss, or precisely the mean heat loss due to different thermal paint types and alpha equal to 0.05. Again, what you need to do first is to get the level total and the grand total, as well as listing down the level sample sizes and the total sample size as follows. Next is to calculate the three sums of squares using the available formula, which are the total sum of squares SST, the treatment sum of squares SSTRT, and hence the error sum of squares SSE. After obtaining the sum of squares, you can then insert these values in the ANOVA table as shown in the subsequent slide. After calculating the sums of squares for task 6.1, now you can construct the one-way ANOVA table and insert the sums of squares in the correct cells of the ANOVA table. Please make sure you follow the correct order of the table, where the first column is the source of variation, followed by the second column, which is the sums of squares. The third column is for the degrees of freedom, where you can identify the total degrees of freedom first, which is 12 minus 1 given by 11, followed by the treatment degrees of freedom given by 3 minus 1, which is 2, and the balance is the error degrees of freedom given by 9. The fourth column is for the mean squares obtained by dividing the sums of squares values in the second column by the corresponding degrees of freedom in the third column. And finally, the last column is for the value of calculated F ratio, which is the test statistic value used in this one-way ANOVA, calculated by dividing the mean square due to treatment, which is MSTRT, by the mean square error MSE. Using this calculated F ratio, we can now complete the solution for the task question as shown in the following slide. Continue with the solution for task 6.1 under the null hypothesis H0. mu1, mu2, and mu3 are all equal, whereas under the alternative hypothesis H1, mu is not equal to muj for at least one ij, for I or j equal to 1, 2, or 3, and I is not j at the same time. The decision rule is to reject H0 if the calculated F ratio is greater than the right-sided critical value, which is F0.0529, given by 4.26 from the statistical table booklet, page 44. By comparing the value of calculated F ratio with the critical value, we can see that the F ratio is obviously smaller than the critical value. Therefore, you can decide not to reject the null hypothesis and conclude at alpha equal to 0.05 level of significance that there is no significant difference in the mean heat loss due to different types of thermal paints. Having done two working examples on performing a one-way ANOVA, which is analysis of variance, we are at the end of part 2. Let's check on the learning objectives you should be able to achieve by now on this chapter. By now, you should be able to achieve the first 4 learning objectives, where the first and the second should be achieved at the end of part 1, whereas the third and the fourth learning objectives should be achieved at the end of this part 2. What about the fifth and the last learning objectives? These learning objectives will be fully covered in part 3 of this chapter. Until then, Assalamualaikum warahmatullahi wabarakatuh, and I'll see you again in the last part 3 very soon. Thank you for watching.